Or have discussed electrostatic statics. Then another approximately case of electrostatic field, we have observed that the static charge definitely is the electric field. Also, electric field dominantly function of, and in other words, magnetostatic strong current can produce magnetic field. Magnetostatic, so whenever a steady current flow there in right conductor or a coil, that definitely a stationary magnet, that stationary is not a varying with respect to time, remains constant. Stationary magnet. Steady current or a DC current uses stationary magnetic field or a constant. The magnetic field magnitude remains constant, not changing time. That is the magnetos. So current flow or a charge in motion always produces mean and also uh, analyzed and field intensity, flux density, and magnetic density, kind of flux, conductance, Peirce Biot-Savart law, of course, Maxwell's equation for the. Also, we summarize the uh, Maxwell's equation, four Maxwell's equations for electrostatic and magnetic. Then we have at the last time varying field. What is this time varying fields? So obviously, as you can, as the title suggests, time varying fields, the variation in the magnitude with respect to time. Also, the addition to the variation, the magnitude with respect to time, there is definitely a propagation wave, electromagnetic wave. So is popularly known as electromagnetic fields, electromagnetic wave, electromagnetic radiations. So the terms we use with respect to electromagnetic waves or electromagnetic fields, radiation. This electromagnetic wave is the popular time varying field, actually basis for all our advances, right? So generation, from the generation that step up and age, and fact in that it in the fields as well as the wave propagation and any medium, right? Any medium, even in the air. Communication as well as many uh, things, many research begins with the time varying. Faraday started his experiment with the time varying field. That is what we first study in time varying field. What is Faraday's law applied to time varying field? So there is some modification in the two equations. mainly around the line integral voltage around the closed path is line integral of E dot dl is not equal to 0. It is something else. We will now go for time varying fields. Note that one. What is the definition of this time varying electromagnetic fields or electromagnetic waves or radiation? Electromagnetic field is the study of electromagnetic waves or a radiation propagation when the periodic time varying magnetic and electric fields produced under time varying current. It's very important to note electric and magnetic time varying magnetic and electric fields definitely produce due to the time varying current, right? This is very important. Time varying current can produce both time varying electric field and magnetic field. That is what we call as the electromagnetic fields or waves or radiation. That is also, in addition to variation, there is a what we call as a propagation. Remember this. There is a propagation as well as the variation of the magnitude of electric and magnetic fields with respect to time. Let us see what is. Example, radio waves, microwaves, infrared rays, visible light, ultraviolet rays, X-rays, gamma rays. These all comes under the electromagnetic waves, right? Right. So electromagnetic waves is used in propagation of wave from one point to another point, the air or in a optical fiber, that is called as a waveguide. Optical fiber or UV rays, infrared rays are used in many sensors. UV rays, X-rays are used in medical fields and so on. Right. So electric field and magnetic field are now not just the function of space, it is also in addition function of time. So far in all the cases, the electric field is function of x, y, z. Magnetic field is also function of x, y, z in Cartesian. So we just happy to write that in just Cartesian coordinate system. But in addition to that, it is also function of time. So we can write electric field as E bar is in bracket x, y, z, comma t. One more term is there, t. Also, magnetic field intensity as a function of x, y, z, t, or the magnetic field flux density B bar is equal to as a function of x, y, z, and the another parameter t. Okay. The time varying fields or waves are usually produced by time varying currents such as sinusoidally varying currents, square current wave, rectangular current wave, so on. So any alternating current can produce, that we call as a time varying current, can produce the time varying fields. So both electric and magnetic. So together we call that as electromagnetic fields. Right. So most of the time we analyze with the sinusoidally varying current, and hence it produces sinusoidally varying electric field as well as magnetic. Let us now begin with the Faraday's law. So Faraday started his experiment in the time varying field. So he came out with the famous electromagnetic induction laws of electromagnetic induction. This is utilized, and mathematically this is represented by Maxwell later, right? So Faraday he conducted experiment, stated famous laws known as electromagnetic induction, laws of electromagnetic induction. This is later, it is mathematically represented by Maxwell, and later on, so that was used to in many applications. So because of his contribution, Michael Faraday is called as father of electricity, right? So he is the first who visualized it is possible to generate electricity in the magnetic field, right? So that is why he is called as father of electricity. So he was invented this in the year 1831, right? Let us now go for the Faraday's law. So first one is this. So he has considered a coil and a magnet. Okay. Note carefully observe here. I have taken this from some net. So there is a animated figure here. So North Pole is moving to and fro inside the coil, right? A coil is there, and there is a, and you can even find the direction of the current flow using Lenz's law. In fact, Lenz's law states that the sign of the EMF induced is in such a way that it opposes the very cause of it. What is causing this? The EMF induced is because of the flux linked with the coil, right? The current flow in the coil is produces its own magnetic field such that it opposes the field produced by the magnet. That is what we mean by Lenz's law. Anyway, I'll come to Faraday's law first. The rate of change of magnetic flux linked with the circuit or coil induces an EMF. The rate of change of the magnetic flux linked with the circuit or coil induces an EMF. Note that rate of change. There is a change in flux with respect to change in time. It is possible only if suppose the magnet is stationary, you cannot expect any EMF induced in the coil. Very clear. The rate of change of magnetic flux is possible only when we move the magnet to and fro. Then only the rate of change of flux linking with the coil is possible. Otherwise, it becomes, so there is a, the, as we know that the magnet produces a stationary magnetic field, right? The bar magnet produces stationary magnetic field. So if the stationary magnetic field and of course the magnet is held at some point, then there is no rate of change of flux. There is no relative motion. What I can say? There should be some relative motion between the magnet and the coil. Then only you can expect rate of change of flux linkage. Otherwise, if magnet is also stationary, not moving, and the coil is also not moving, what is the EMF induced in the coil? V EMF is 0. You can write that. Now there is a motion, and as I said, the magnetic, the direction of this you can always determine using the Lenz's law. Yeah. So the, according to Faraday, V EMF is equal to rate of change of flux linkage, d by dt of lambda. Lambda is n pi. Okay, you have seen that one. So that is n is number of turns. Okay, so that means